This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, let's start the lecture today. It's the second time you're stuck with me. Hopefully it's the last time, at least for this semester. So today we are going to talk about invariance and really temporal logic. How many of you have heard of the term together, temporal logic? Has anyone heard of it before? Have you heard of propositional logic? Have you heard of logic? Good. So at least there is a word that we can start with. Temporal, can someone tell me what temporal means? It's related to time. Yeah? Okay. So the idea is that it's a sort of logical set of statements that try to explain something across time. Okay? So that's the starting point. It's a good picture to have in mind. What is another family of systems that really work over time? Dynamical systems are things that explain and show a certain behavior over time. So temporal logic is really a tool to make logical statements about systems that evolve in time. Okay? So that's the mental picture that you should have. It's really based on chapter 13 of your textbook. Again, I recommend that you go and look at it. There are other textbooks as well that talk about temporal logic, but Lee and Sechia do a good job of it. First, you have to ask the question, what does it mean to say a design is correct or not? Right? It's again like the last time when we talked about a scheduling algorithm is optimal. You have to understand, what do we mean by that? What does it mean that something is correct or not? Well, it's the correctness is we define however we want it to define. So the key term there is a design is correct with respect to a bunch of specifications. Specification is just another word for requirements. We want our system to behave in a particular way. That's the sort of specification. If you manage to design a system that exhibits those sort of behaviors, then it is correct. So these are the jargons that we are going to use, and this is what we mean by that. There's a code that I really like, is if you start designing a system without knowing what it's supposed to do, the end product is neither good, or bad. It's just surprising. Because we never designed it in a way to satisfy sort of specifications. Later on, when you go and do your capstone project, that would be your biggest problem with a lot of it. You don't quite know what are you doing, you just do stuff, then sometimes interesting things happen, and then you're excited. But it's a roller coaster of emotions. You don't want to do surprising stuff. You don't want to be surprised by your own design. You have to think about it. And to make sure that nothing is surprising, running a few ad hoc tests is not enough. So back to the Yiddish problem we have. I cannot say something is behaving properly if I just run 5 simulations. I cannot say it even if I run 10 simulations. Make it 100. I cannot make a valid statement that something is going to work all the time if I just see a bunch of examples. So we need a way to guarantee that something works properly. It is especially important when we talk about safety critical applications. When you're flying an airplane, you do not want it to crash because it wasn't designed according to specifications. The most recent example was the 787 MAX. That was a specification problem. some sensor output was getting redirected into the system, it was faulty, and they couldn't reset the system. It was a classic example of bad design and a design that wasn't meeting safety specifications. That's something else that is important as well. I mean, we can always be vague and make general statements and show pretty pictures, but in the end, it's nothing but BS. Try to be specific and very particular about the claims you make, and try to meet them in a systematic way. That's fine. I mean, for those of you who maybe know him, was a physicist in the starting from around 40s, and he died late 80s. So again, it's very important as engineers. It's very important that we are very specific about what we are claiming that we are designing, and then go about and design it and deliver the result. This is just one example of many, many times that people didn't design systems according to specifications. And especially now, a lot of systems that we are using and critical systems that we are using, for instance, medical devices, they run software underneath. And by construction, they are dynamical systems that the behavior changes, the environment changes. So what we want is them to always behave in a particular way that doesn't cause problems. This is just an example from 2004. When the measurements really resulted to more than one patient, multiple patients, to be in critical conditions. Okay? So that's just one example. We can construct these examples many times because there are as many bad designs, because you always hear about bad designs as well. Whenever something happens, the first question to ask is, what was wrong in the design and the development part of that particular product? All right. So in the design process of a system, in this sort of an embedded system, that this idea can be applied to any system. First, we start with some specifications, what we expect the system to do, what are the requirements of the system. Then we go around and do a bit of verification. We design it, how does it meet the requirements of the design? Then we go and synthesize a realization of the system. So that's what we call controller synthesis. So to really realize the system in the operating environment. And if we stick to the specification, then everything is well, then we really don't need to worry about it. So, but we are talking about specification. Now, first we have to be able to specify what we want to do. All right? So this is another way of explaining the previous slide with the language of boxes and pictures. What we want to do is we have some model of the environment. Hopefully we paid enough attention in our maybe control systems class. We learned how to, at least basis of modeling, we understand what models are for. Let me ask you a question. Can someone tell me what models are useful for? Approximation is a bit better. It's about capturing a very complicated phenomenon as a simple thing that you can understand. Now, how important it is to have a very exact model. Maybe. The question is incomplete. I have to say, what do I want to do with that model? Can we ever have an exact model? No, it's a fool's goal to look for something that is super exact. The question should be always asked, is this model exact enough for what I want to do? Okay, so that's something that it helps to be reminded of every now and then. All right, so we have models, we constructed differential equations, difference equations, whatever. There are some models given to us. We have a bunch of requirements. It's the same different word for specifications. We have a system that verifies if, for example, given that system described by that model and those specifications, is it even possible to meet those specifications? It's the first step of a sanity check. So really, are the specifications satisfiable or not? Either yes or no. If it's not, hopefully we gain some information. Here is just the one key term for it is error phrase. It's really just a counterexample of when the specifications were not satisfied. Hopefully we go and reiterate the model, or we revise our specifications. If yes, then we are good. At least we know it is possible. So let's go and synthesize the system. Now, to be able to feed the requirements, we already know how to describe models. We use mathematics, the language of mathematics, as a tool to describe models exactly. What are the two main tools that we use? There are differential equations and difference equations. Okay? So we have that language set down. So we need another similar language to be able to express requirements and the specifications as well. So that's what we are going to focus on. So one way of expressing these desired properties is over time. Again, temporal element is to use temporal logic. So it's really, for example, if you want to describe the behavior of a finite state machine, we need to use the language of temporal logic to describe that behavior. And there are many different flavors of temporal logic. We have propositional temporal logic, that's what we will focus today. There are real-time temporal logic, interval temporal logic, signal temporal logic, etc., etc., etc. But all of them try to do the same thing. They try to explain the behavior of a system over time using some very precise language. Now, why is that? If you go and look up ESA's standard page for designing systems, ESA is the European Space Agency, located in a very miserable part of the Netherlands. So they just write documents like this. These are the specifications that they write. I don't know, the second one. In the good one is this. Whenever the reset signal is asserted, the state machine shall move immediately to the error reset state and remain there until the reset signal is deasserted. What does it mean if you want to design a system? How do you represent this? That's where it's missing. You cannot use natural language. Natural language, by definition, is imprecise. Because interhuman communication is imprecise. You don't need all of us to be precise with each other. It would have been great, but it's not, natural language is not developed for that. So we need another language to be able to express these things in a way that it is impossible to misunderstand them. Okay? So hopefully you're getting half persuaded what we are talking about, whatever we are going to talk about soon. This is another example from your interrupt lecture. So the property that we want to have, for example, in that piece of code is whenever the interrupts occur, and assuming that they can occur infinitely often, we always want to end up here. There is a, let me move this, so We always want to end up in position C. So we have to be able to, again, express this, because this is a finite state machine as well. That piece of code itself is a finite state machine. This is another example. I have a robot that starts from this location. Good. And we want it to end up here. So that's one specification. Maybe we have multiple destinations. We want to hit them periodically. Maybe another specification is not to bump into obstacles. That's a specification. There are more concrete examples of specifications that we might need. Okay. So now let's start. Let's warm up. This is something that the first thing that we have is an atomic formula. Good, maybe. I don't know. Atomic formulas. So these are statements about an input, output, or the state of a state machine at some given time. They worry about anyways, so it's about a statement about a particular input, output, or state at a given time. So for example, if the formula is given like just x, what it means is x is present. So if we are testing for the presence of an output, you say that the formula we're testing for it, that's the formula. So that makes sense for what type of signals? Pure signals. There are signals that either are present or absent. The other one is x is equal to 1. So it's for an input that takes values, or for an output that takes values. Or S can be just state. Are we in state S? So these are the atomic formula that we deal with. They are the. Can someone tell me the meaning of atom? Something that cannot be divided. Is the fundamental component of anything. That's the Greek word for that. So these are the building blocks of any other statement that we are going to make. There is nothing lower. There is nothing more granular, really. There are now propositions, which is really another word for true or false statements about a particular state machine. Some signal or state at some given time t. Now we can combine these atomic formulas to construct propositional statements. These are the things that probably you've seen it in high school, I don't know. There are things that we combine by an AND operator. P1 and P2, it means a condition that both P1 and P2 are satisfied. P1 or P2 is the next one. Either of them is satisfied. P1 then P2 is if P1 is true, then so is P2. The negation of a particular statement is, the negation is true if P1 is false. Negation of P1 is true if P1 itself is false. So these are now the examples of propositional statements. We can start combining atomic formula and then construct propositional statements, then combine propositional statements and keep building on top of each other. So that's just propositional logic. seen a version of it before. I would be very surprised if you haven't. Now, there's another term that we need to start using. Execution trace, or sometimes just trace. If I have a finite state machine and let it run in each time step, we can record the state that we are in, the input to the system, and the output of the system. If I concatenate all these three together, we get a tuple. Now, in the next time step, I record the same thing. Next time step, I record the same thing. If I just put them back to back, so each of these Q i's or j's corresponds to that situation, and I record the whole thing, is a trace, is an execution trace of the final state machine. That's just the name that we give to this sequence. So we can always also write it like this as well. We are in at some state S naught. We are given some action, some guard X naught, some action Y naught, so input X naught, output Y naught. We go to state S1, and we keep going. That's another way of expressing the same sequence. The idea is that it's a sequence of input-output state triples. There's another word for it in the context of dynamical systems. This thing is called the trajectory, or sometimes called the behavior of the system. Again, different communities give different names to the same idea. It's important to understand that if you go and read a book and they start talking about trajectories, don't say, oh, this is a whole new branch of science that I'm seeing. Same thing. Just keep them another name. Okay. So now there is an element of time, because there is a precedence between each of these Qs. First Q naught happens, then Q1 happens, then Q2, etc., etc., etc. Okay? So now we are getting to the concept of time as well. Now, if I'm given a propositional logic statement, I say that formula P holds for the whole trace. Now, that's the weird thing for the definition, but hopefully it becomes a bit more obvious later. We say a formula holds for the whole trace if it only holds for the first element of the trace. That's how we define it. So if I look at the whole sequence of trajectories, I test the first step against the formula I have. If it satisfies it, then I say the formula satisfies the whole trace. Okay? It's the definition. That's how we define it, because it allows us to build things in a bit. It's always if and only if as well. Who doesn't know what I mean by if and only if? So everyone knows necessary and sufficient conditions? Okay, good. Just in case you are a bit shy, if and only if is that if I start from the first statement, the second statement is true. And if I start from the second statement, the first statement is true. So that's this P, if and only if Q. Okay, as I said, it's a bit odd, admittedly, to define, to given a trace with all these other elements, and we only focus on the first element of the whole trace. But that's how we can put things together using a bunch of operators. Okay, now, if I have a statement, let's see what type of statements can be made about a trace. We say a formula holds for this trace if it is true for the first element of the trace. So far, so good. Then we have these four operators, G, F, X, and U. G stands for globally, F stands for finally, X stands for next, U stands for until. Now let's see what each of these things mean, because this is the most important slide of this lecture. So if we say G5, we are saying that phi holds for any suffix of the trace. Now, what is a suffix? A suffix is if I chop the trace from any point, I end up with a suffix. Suffix is something that you add to the end of something. So, for example, if I look at this here and just look at a sequence that starts from Q1 and keeps going, that's the suffix of the original trace. Another suffix is something that starts from Q3, for instance. So these are different suffixes. So G holds for every suffix of the trace. So whenever I start it, P should satisfy. What is another way of saying it? It means P is true for every single element of the sequence. Right? So by just this sort of looking at different suffixes, I'm really just testing every single element. Finally is a similar thing as well. It means there is at least one suffix that the proposition P holds for. So it means there is at least one element somewhere in the trace for which P holds. We're going to see examples of these briefly, but that's the idea. We have X phi is true if I'm given a trace, I forget about the first element, and I test for this new particular suffix. So it means the next stage satisfies the condition that I'm interested in. Until is Q1 holds for all suffixes until something else happens. For example, if I want to say phi1 U phi 2 for this whole, there is a portion of the trace for which phi 1 is satisfied, and then here phi 2 starts being correct, then I don't care about what happens next. So until phi 2 is satisfied, phi 1 continues to hold. Again, here P is either a propositional logic formula. P is a propositional logic formula, and phi is either a propositional logic formula or an LTL formula. So that we can compose this sort of formula inside each other as well. Just an example, again, another way of seeing what these things mean is if I have some trace and I look at all the possible suffixes and they keep going. GP means P should hold for every single one of these suffixes. Based on our definition, we said P holds for a trace if it holds for the first element. So it should hold for each of these elements. In the original trace, it means it holds for every single element of the original trace. If P is a propositional formula, then we call it an invariant. Again, it's a name. So globally, some formula holds. That formula is invariant. It doesn't change. Okay. Finally, or eventually, or future, these are again different names given to this other one. It means If I go and look at all the possible traces again, there is at least one trace for which the formula holds. So here, this example is it holds for this trace. It doesn't matter if it doesn't hold for any other one. There exists at least one suffix, one subtrace for which the formula holds. Eventually, there is a state somewhere in the future that the formula holds for it. Okay. Now, as I said, we can compose these things in different ways. For example, I can have operators globally, and then that it operates on another propositional logic, but the second one is an LTL formula as well. Let's unpack this. So first we say globally. So globally, whenever X happens, then at some stage in the future, Y should happen. It is eventually followed by Y. So that's how we can construct rather complicated statements. So really that means whenever we observe X, eventually we are going to observe Y. Okay? Again, it's a language that allows us to state these sort of statements. Again, to see just the picture, whenever I see X, eventually Y holds. So it should hold for any trace for which X holds. There is a suffix in that trace that Y holds as well. So in this example, we assume X holds here, and in that suffix, there is another suffix inside for which Y holds. Now, we talked about the trace for a particular behavior of the system. If you want to say a particular system satisfies a formula, you have to go and test all the possible traces. Test the condition on all possible traces. If the condition is satisfied, then we say the finite state machine itself satisfies the LTL formula. Now that's the biggest challenge of any system design, to make sure that a property holds globally for a system. And a lot of active research is done to be able to come up with tractable ways of this verification process. Sometimes we use the particular structure of the system. Sometimes we use different tools. Sometimes we devise tests for worst case behavior. So that's an open area, but that's what it means if an LTL system, a finite state machine satisfies an LTL formula. So it means for any trace of the system, the LTL formula is satisfied. Example. This is a simple finite state machine with actions and guards. So the question is it true that whenever X happens, eventually Y happens? Think about it for 1 minute. Okay, let's ask yes or no. Show of hands, who says yes? No? Okay. Why yes? You're the closest. Yeah.
It's because if like X occurs, state A goes to state B, and output goes to B, and then it's always true that Y is gonna occur to go back to A.
Okay. The idea is correct, but you really used wrong words for it. A, action X happens, so input X happens. If X doesn't happen, we don't transition out of it, we remain A. If X happens, action X happens. There is no output associated with that transition. We end up with a state B. In state B, we always transition back to A, but present output Y. Okay? So this is yes. Now, a very similar system, exactly the same proposition. Now, based on my tone, you would say, oh, no, the answer is no here. But why?
You don't know which path to take.
Correct. Non-determinism breaks down the system. Transition to state B, and then I can construct a viable trace that ad nauseum stays in B. So that's the counterexample trace. That means if I go and want to redesign my system, that's the loop that I have to break. Okay. The next operator. So we say XP holds if I go and check the trace starting from the next state, input output state triplet. If P holds for that new trace, then XP is correct. This is really used to construct statements like, if something happens, immediately we want something else to happen. That's where it's useful. And then P1 until P2, what it really means is okay. P2 will hold, let's assume P2 holds for some suffix. For all the previous suffixes, P1 must hold. So P1 keeps holding until P2 holds. It doesn't preclude the fact that P1 might continue to hold. But the statement is about until P2 holds, P1 holds. That's the until operator. These operators G, F, X, until, I think is always used as U, is another set of symbols used for them. So that we can use square for globally, diamond for eventually, and circle for X. So if you really want to write completely the things that people think that you are the smartest person ever, use these. So that's the that's the notation used in the book by Allor. The other book that I put on the previous slide, which I think is a good reference as well. But the meanings are the same, it's just a different symbolism. Notation, right? Now, if we go and combine these statements, we can construct more meaningful sentences because it's a language. We start from the basics, the fundamental blocks that were the atomic propositions, atomic formula. Then we constructed logical propositions. Then we constructed temporal logic, LTL formula. Now we can keep combining them. We can construct sentences now. These are a bunch of examples. Let's see what they mean. It means always, eventually P happens. So if I look at any trace, in that trace, eventually P happens. I'll go and look at another trace, a suffix, eventually P happens. So there are infinitely many suffixes. In each of these infinitely many suffixes, there is at least one occurrence of P. So infinitely often, P happens. The next one is just flipping the position of eventually and globally, or eventually and always, becomes eventually always P is true. It means if I look at the trace, there is a point in the trace that from that point on, P holds. That's how we describe the steady state behavior of the system. We are controlling something, we want it to go to track a set point. We always eventually always we want to satisfy tracking that set point. So that's the steady state behavior in the language of temporal logic. Then there is another property called request response. So that's the always when P happens, eventually another statement here Q happens. Is the request response. Whenever the request P is made, you are going to respond to it in some time in the future. So in an embedded system, this is really the case that we want to guarantee for interrupts, for instance. That's a property that we are interested in. Another example is this. At some stage in the future, or in the trace, when I say future, really, sometime in the trace, if P happens, 2 steps later, Q happens. Because I can keep putting X's back to back. They compose like that. So all these 4 operators, they express properties across the trace. So we can again compose them however we want. This is another example. Sorry. And sometimes we can express them in their equivalent formulations as well. So if I want to, for example, say always phi, it is equivalent to saying never, eventually, phi doesn't happen. So there is no trace that phi doesn't happen in it. It means in every trace phi happens. These sort of equivalences allows us to write things, if you can think of it, we can factorize statements. We can write f in terms of u, the until operator, which is very simple. True, just some vacuously true statement holds until the statement that we want to hold. Same as eventually the other statement. And because we have this, I can always go back, I can write, I mean, this is some relationship between f and g. something that we cannot do is we cannot state x in terms of the other three operators. Because otherwise, probably we wouldn't need it. Because none of those operators really have this hard condition on when. X is the only one that exactly determines the next observation should satisfy the property that we are interested in. Okay? Now, important things to remember, or if you want to make a lot of P sounds, some points to ponder. It's really about, if I write the specifications, we are really just writing the properties that the system must or must not have. It really doesn't say anything about what those properties mean. You're just writing properties. It's just a way of expressing properties. Again, it requires the human judgment, or in our case, engineers, to decide if that particular specification is something that is needed, or is necessary, or sufficient for what they want to achieve. Writing specifications in a fancy language doesn't remove the need for us to think about what they mean. The sort of language that you're talking about just allows us to be precise in a way that is not open to any interpretation. Okay? And really getting the specification right is the biggest design challenge. This allows us to, after we spend a lot of time thinking about the specification, it allows us to state those specifications exactly, so that we don't mess up the design in the implementation stage by misinterpreting what we are supposed to do. Okay. There are research directions, there are active research directions. Sometimes we want to reverse engineer a particular requirement by observing the traces of the system. That's the question of reverse engineering. Automatic translation of natural language to temporal logic specifications, another area that people are thinking about. And then this last bit is when there is no unique way of specifying these sort of requirements. But the question is that, is it possible to come up with the most efficient way of expressing them so that when we want to go and realize the system later, we can do it in a tractable manner. So we don't get stuck in a lot of computation. So two examples of time. Yeah. So just two exercises to think about it. Let's try to do the first one. Let's read it. Whenever the kabuki is at the ramp edge, so at the cliff, eventually it should move 5 centimeters away from the cliff. So there are two propositional statements, P and Q. How should I represent this requirement? So whenever, always, P, then eventually Q. Okay, so that's one specification there. There is something implied there as well. To be able to satisfy eventually Q, it means that we didn't fall off the edge. It captures that property. Otherwise, we cannot satisfy. In a cruise control, maybe, whenever the distance between cars is less than 2 meters, deactivate cruise control. So here we are saying P is true whenever the distance is less than 2 meters, and Q corresponds to the case that cruise control is active. So how can I write this now? There is a global element. P is happening. Then what? Negation of Q. Let's go back to the beginning. Let's look at European Space Agency's specification. Okay. This is similar to what we had. Okay, the last one is a bit interesting because it uses a bunch of other things. Okay, so we call this a statement P. We call being in the states error reset Q. Whenever P we have to interpret immediately somehow. Yeah, we can use X. But maybe we define immediately as the next, either the next state, the next step, or the second next step. It depends what we mean by immediately. So let's use X. Until D asserted. So if P is asserted, D asserted is negative of P. We can have this as well. Sorry, I didn't mean to say and. Or maybe X. So this interpretation is immediately either means next or after next. Try to rewrite the other ones using this sort of specification as well. It really allows you to think about why. It's again, this, and really the whole branch of mathematics is about stating things precisely. That's the most important point to remember. Stating things like that, remove the possibility of misinterpreting a statement. Okay? Thank you. Maybe see you on Monday. I don't know if Gavin cancelled Monday or not. But see you.